Hi guys, Mrs. Rossi here. Today we're going to be talking about water and aqueous systems. You have your note sheet to follow along with, so as we're going along, feel free to pause the video if you need to, go back if you need to, and make sure you answer all the questions on that note sheet. As we get started, I want you to think of some things that we use water for. So water's all around us. We know that lots of our planet is made up of water. So what are at least 5 things that we use water for? Think about it and write them down on your sheet. The rest of the front of that sheet is review as well. So is water ionically or covalently bonded? After you pick, it's because hydrogen and oxygen are both. Water is unique because it's a special type of bond, one of those intermolecular forces we talked about earlier this school year. And then I'm looking for a picture of a water molecule using its shared electrons. So about 72% of Earth's surface is covered in water. We know that water exists in oceans as salt water. Fresh water only makes up about 2.5% of all of the water on Earth. And then if we break the fresh water down that we use, 79% of it is frozen. 20% of that 2.5% is groundwater. And then only 1% of that 2.5% of fresh water is in lakes, rivers, and streams around the world. And then there's 0.001% of water in the atmosphere. All right, so hopefully going back to things that water is used for, agricultural uses of water accounts for 70% of all water consumption in the world. 20% is used for industry, so think like power plants or nuclear power plants that use water as cooling systems, and then only 10% of water worldwide is used for domestic use. In industrial nations like ours, industries consume more than half of the water available for human use. So think about all the animals for agricultural use, watering plants for agricultural use, and industry. We talked about power plants, domestic uses, all the things that we use it for. So drinking water, showering, going to the bathroom, all of that stuff accounts for water use as well. All right, so some of those unique properties of water, we should have that it's covalently bonded. It's a polar molecule, so meaning that oxygen is more electronegative than the hydrogen, so it pulls those electrons a little bit closer to it, and it can participate in hydrogen bonding. Remember, hydrogen bonding isn't a real bond, it's just an attraction because of the difference in electronegativity. Hopefully your water molecule that you drew for number 4 looks like this. So we have the shared electrons down here, hydrogen only needing 2 to have that full outer shell, and oxygen needing 8 to have a full outer shell. Here's an example of the electronegative part. So we know oxygen is more electronegative, so it becomes slightly negative, and hydrogen, because it's pulling the electrons away from hydrogen, becomes slightly positive. So when hydrogen bonds, the positive and negatives line up together like you see in this last picture. All right, water properties. Water has some really unique properties that are actually really benefit us. We previously have talked about surface tension. Water has a very, very high surface tension. Surface tension is the inward force or pull that tends to minimize the surface of an area of a liquid. You have definitely seen this when you did the drops of water on top of a penny. You were able to pile lots and lots of drops there, and it made that curvature type shape on the top of the penny. This is also the same reason that some animals are able to walk on top of water, like you see with this bug right here. It's also the same reason that droplets form when it rains on top of your car, because that water would rather be with itself than interact with the surface of your car. Here's our favorite basilisk lizard, and this guy takes advantage of the surface tension of water as well and is able to run across the top.
Some young Costa Rica.
We'll go back.
young Costa Rican basilisk lizards are looking for food. Basilisks have been nicknamed the Jesus Christ lizard. Why? This adult male, probably the father of the young lizards, can't tell us. Nor can this female, exclusive property of the territorial male. It has nothing to do with the feeding habits of the basilisk, which consists primarily of insects and berries. This predatory reptile will help reveal the secret as it stalks the young basilisk. The basilisk is called the Jesus Christ lizard because it can walk, well, really run on water. It bicycles its hind legs, and the tail becomes a counterweight. We can't know what the snake is thinking. Did it really want to eat the lizard, or did it just want to show?
All right, so there's one example, and something else you've also seen is when we did the pepper on top of water during lab, you put the pepper on top, the pepper was able to float because the water would rather interact with itself than the pepper that we put on top, but as soon as we added the drop of soap, the pepper spread out. That soap that we put on there was acting as a surfactant. So a surfactant is how you can decrease surface tension. So usually soaps or detergents are surfactants, and that's how you kind of break the surface tension of things. It's how your laundry detergent works. It's how your dish soap detergent or dish soap works to clean and break down on the grease or stains or whatever you have on your clothes or dishes. Hydrogen bonding is also a big part of another property of water, which is its very low vapor pressure. Vapor pressure of a liquid is caused by the molecules that escape the surface of a liquid and enter the gas phase. So we're talking about when it goes from the liquid phase to the gas phase, so evaporation. So water doesn't really evaporate that easily. It takes a lot of energy, a lot of stuff has to get put in to make it evaporate, which is really good for us because since water has such a low vapor pressure, we don't have all of our water supplies, our freshwater supplies, getting evaporated into the gas phase very quickly. We'd have a lot more droughts, a lot more issues watering all of our crops, feeding all the animals, cleaning ourselves, disposing of things if water had a really high vapor pressure. The next property is specific heat capacity. Water has a very high specific heat capacity. Specific heat capacity is the amount of energy needed to raise the temperature of 1 gram of one substance by 1 degree Celsius. Water having a really high specific heat capacity is also really good for us because it means if it's really hot out on a day and you go to hop in the pool to cool off, the water will still be cool. It's going to take a lot of energy to warm up that type of stuff. It keeps our fish alive in the oceans. It keeps our fish alive in freshwater, all the animals and microorganisms that are in there alive because it takes so much energy to heat up 1 gram of water by 1 degree Celsius. Water specific heat capacity is 4.18 joules. Joules is a measurement for energy, abbreviated with a capital J. So all of this is leading up to, and the special properties of water are aqueous solutions. Aqueous solutions are just water samples containing dissolved substances. So the base of whatever it is water. So some examples: when you make hot chocolate on a cold night, water based, so it's an aqueous solution. Most fruit juices that you drink are water based, so they're aqueous solutions. Even the water, our tap water that we drink, is actually a mixture because it has different stuff. It's not exactly just pure water. Salt water, all the oceans where you go swimming in the summer, aqueous solutions because water base with other stuff dissolved in it. All right, so when you have an aqueous solution, you have something called the solute and something called the solvent. In a solution, the dissolved substance is called solute, so the thing that gets dissolved. For example, in salt water, salt is the solute because it's the thing that gets dissolved into the water. The thing that does the dissolving is called the solvent. So in salt water, water is your solvent because it dissolves the salt. All right, so let's take a look at these three. We have sugar and tea, powdered lemonade mix, and chocolate syrup and milk. So our solute, the thing that gets dissolved, sugar and tea would be sugar, and the solvent would be the tea or water, pretty much. So this would be an example of an aqueous solution. For powdered lemonade mix, you usually take your powdered lemonade, you take water, you mix it all together. So your solute, the thing that gets dissolved, would be the powdered lemonade. Your solvent is going to be water. Chocolate syrup and milk, so you're making some chocolate milk as your after school snack. Your chocolate syrup is going to be your solute, and your solvent this time is going to be milk. So this wouldn't be an aqueous solution because milk is not water, and water has to be the solvent in an aqueous solution. So you may have noticed that some stuff dissolves really easily in some substances, and sometimes something won't dissolve at all. There is a way to figure this out, and it's really not that difficult to do. Sometimes there is a certain rule that we like to use in chemistry to kind of figure out, will it dissolve or will it not dissolve? So, as a rule, polar solvents dissolve ionic compounds and polar molecules. Nonpolar solvents dissolve nonpolar compounds. A much easier way to say this, and what you typically hear in chem classes, is like dissolves like. So if you have something that's polar and another thing that's polar, it will dissolve. If you have something that's polar and something that's nonpolar, it won't dissolve. If you have two things that are nonpolar, so a nonpolar and nonpolar, it will dissolve. So like dissolves like. But now we need to figure out, how do you know if something's polar or not? You need to know the electronegativities. So here is a periodic table with all the electronegativities of the different elements listed on it. You also have one on your note sheet. Here are the steps that we're going to follow to figure out, will it dissolve? So we're going to have a solute and we're going to have a solvent. And that's the first thing you need to identify. Identify what is the solvent and what is the solute. 9 times out of 10, your solvent is going to be water. So that's a really good indicator as to what is doing the dissolving. Then you need to figure out, is the solvent polar or nonpolar? And is the solute polar or nonpolar? So you'll be treating them differently. How do you know if something's polar or not? You're going to use this chart right over here. You're going to find the electronegativity of the atoms involved and subtract them. If it's an ionic bond, so if it's an ionic compound, it's going to have an electronegativity difference greater than 2, so automatically polar. If the difference between the two elements is between 2 and 0.5, it's polar, and if it's under 0.5, it's nonpolar. So you're going to use the electronegativity table to figure this out. So you figure out, is the solvent polar or nonpolar? Is the solute polar or nonpolar? And then step 3, like dissolves like. If both of them are polar, it dissolves. If both of them are nonpolar, it dissolves. If you have one that's polar and one that's nonpolar, it will not dissolve. All right, so let's try this one together. So we have water, H2O. You look at the electronegativity for hydrogen first. We have 2.1. And then you look at the electronegativity for oxygen, 3.5. So you're going to do 3.5 minus 2.1. And when you compare it to your electronegativity difference chart, so 3.5 minus 2.1, you get a difference that puts you in that polar covalent bond range. So it is a polar molecule. You're going to do the same thing with sodium chloride. Notice sodium is a metal, chlorine is a nonmetal. I know this is an ionic bond, so automatically polar. Since it's polar and polar, will it dissolve? Yes. All right, so here we have water again. Remember, it's H, so hydrogen, 2.1 for an electronegativity, and oxygen, 3.5 for an electronegativity. It's a polar molecule. You're going to do the same thing with methane. Methane is 2.5, or carbon is 2.5 electronegativity, and hydrogen is 2.1. So there's only a difference of 0.4. Methane is non-polar. Since methane is nonpolar and water is polar, it will not dissolve. So methane will not dissolve. I want you to look at the rest of your paper. Number 17, 18, and 19 are all practice problems. So use your electronegativity chart and the chart with the electronegativity difference range to figure out if they're polar or nonpolar, and then if they will dissolve. The next thing I want you to do is complete the review on the bottom of everything that we've done on this worksheet.